Hello everybody. This is lecture 5 in M8 2H3 linear algebra, and this is the pre-recorded version of Wednesday's lecture in week 3. So our topic today is systems of linear equations, and our goal is to develop a systematic way of solving systems of linear equations using matrices. So we'll just begin with a quick recap from the end of last week. What is a linear equation? What is a system of linear equations? And what does it mean to solve such a system? So basically, a linear equation in some variables is something that looks like the equation here in this slide. It's got a coefficient, which for us would be typically a real number or an element of our field, whatever it is, for each of a bunch of variables. And so this linear combination of the variables is equal to some fixed value, which usually is written on the right-hand side of the equation. So anything of that form, 2x plus y equals 3, 3x plus 4y plus minus 7z equals 10, anything like that. So what makes it linear? I guess it doesn't have any products or expressions involving the variables, apart from just a linear combination of them with some coefficients. And so a solution of a linear equation is a collection of values that you can assign to the variables that make the equation into a true statement. So for example, with this particular equation, if we put x and y both equal to 1, we get 2 times 1 plus 1 equals 3, which is a true statement. So x equals 1, y equals 1 would be a solution of that equation. X equals 2, y equals minus 1 would be another one. X equals 2, y equals 2 would not be a solution, because that would make 2x plus y equal to 6, which isn't equal to 3. Okay, so that's what it means to have a linear equation and to have a solution. Okay, and as we know, of course, for an equation like that, the set of all solutions forms a line if you graph it, if you graph the coordinates of all points, which are solutions of that equation in the plane. Okay, so that's a single linear equation. A linear system is a collection of potentially more than one linear equation in the same variables. Okay, so a linear system is a collection of linear equations in the same n variables, whatever number of them. So here's an example of a linear system with 2 variables and also 2 equations, 2x plus y equals 3 and 4x plus 3y equals 4. So of course we can solve this system of equations with an ad hoc approach by just sort of, trying to identify what possible simultaneous solutions of those 2 equations might look like. What it means to solve a linear system is to find all potential values that could be assigned to the variables so that all of the equations would be simultaneously satisfied by the same assignment of values to the variables. And again, as with a single equation, there could be multiple solutions to a system of equations, or there might not be any solutions, potentially. So there's an example. And I guess if we wanted to solve this system using a ad hoc approach, one thing that we could do would be we could take equation A, multiply it by minus 2. I'll just make a remark about what's going on here when we do that. If we multiply both the sides of equation A by minus 2, we get minus 4x minus 2y equals minus 6. So this is a different version of equation A. It's not the same equation as equation A. It doesn't have the same coefficients, but it does have the same solutions. And this is the key point. There are adjustments that we can make to equations that don't change their solutions. And then equation B is still 4x plus 3y equals 4. And the assertion here is that any simultaneous solution of equations A and B must also satisfy these 2 equations. Okay, and that means any simultaneous solution of equations A and B must satisfy these 2 equations and anything that we could get by, for example, adding them together. So if we add these 2 equations together, we would get that 0x plus 1y equals minus 6 plus 4, which is minus 2. So we're saying then that any pair of values for x and y that satisfy both of these equations must also satisfy the equation y equals minus 2. So the value of the y variable there must be minus 2. And once we know that, we can figure out what x should be from, for instance, the equation 2x plus y equals 3. That would tell us that 2x minus 2 would be equal to 3. So that would be equal to, so that 2x would be equal to 5, and x would be equal to 5 over 2. Okay, so essentially we're saying that this pair of equations, x equals 5 over 2 and y equals minus 2, which obviously has a unique solution since it specifies values for both x and y, that this is the only simultaneous solution of the original pair of equations. And we can check that it is a simultaneous solution by confirming that it satisfies both equations. The first one would say 5 minus 2 equals 3, which is certainly true. And the second would say 4 times 5 over 2 which is 10, plus 3 times minus 2 equals 4, which is also true. Okay, so that's kind of what I mean by an ad hoc approach. That's fine, nothing wrong with it. Except to remark that if you had a system of equations with more variables and more equations in it, that would not be so easy to figure out how exactly would you go about kind of eyeballing the equations so that you could cancel a variable out of them and identify solutions for particular variables and identify all possible simultaneous solutions of all of them. So what we're going to do, and this is the theme for the next couple of lectures, at least, possibly the next 3 lectures, is we're going to develop a systematic approach for dealing with all possible systems of equations. And it is a classical, but also kind of modern approach in the sense of how it is used in modern computational applications. And that is called Gauss-Jordan elimination. So it has been around for a couple of 100 years, but it is still very much in use in the most up-to-date computer applications. And it really is kind of the sort of backbone of many algorithms for solving systems of linear equations, which are hugely important in lots of application domains as well as in mathematics itself. Okay, so there's a bit of lingo in this section. One piece of new terminology maybe is this concept of an elementary row operation. And there's also the concept of a row echelon form. And there's the notion of Gaussian elimination or Gauss-Jordan elimination, which we will develop. Okay, here's an example. So here's a system of 3 equations and 3 variables. We want to find all solutions of this system. So we want to find all values that could be assigned to the variables x, y, and z so that all 3 equations would be satisfied. Okay, and again, I'm not saying that this couldn't be done by an ad hoc approach, but it is slightly more complicated at least than the last example. Okay, so if we were to take an ad hoc approach, what could we do? Well, we can do things like we can multiply an equation by a non-zero constant, and that certainly doesn't change the solutions of the equation. It does change the coefficients, but in a way that doesn't change the solutions. We can add one equation to another. And a reason why one might do that would be to maybe eliminate some variable from the result if its coefficients in the 2 equations that were being added together were negatives of each other. So for example, here you might add equation 1 to equation 3 because that would knock out an x from the resulting equation. Okay, but I think it's important to consider what it is that we're doing when we add one equation to another and why that is a legitimate thing to do. So we're interested in simultaneous solutions of all equations. Now, if you add two equations together, you certainly do change them. The solutions of the resulting thing are not the same as the solutions of either of the things that you started with. But it is true that if you have some assignment of values to the variables that simultaneously satisfies a pair of equations, then that same assignment must also satisfy the thing that results from adding those 2 equations together. Okay, so basically, if you have a system of equations, then and you add 2 equations together to get a new one, basically any solution of the original system must also be a solution of this new one. So kind of adding that one into your system doesn't change the simultaneous solutions. So that's why it's kind of considered to be a reasonable thing to do. So what we're going to do now is we're going to develop a technique, a systematic one, for describing our system of equations and for applying operations only of these types, nothing more involved than that, but in a systematic way and hopefully in a clearer way that will allow us to kind of attack any problem of this type, either directly by hand or computationally if it's too big to attack by hand. Okay, so basically what we're going to do, we're going to translate the system of equations into a matrix. We're going to work with the matrix instead of directly with the system of equations, and we are going to basically consider what the operations that we just talked about with equations would correspond to in terms of a matrix. The matrix that we associate to our system of equations is called the augmented matrix. And let me just make one remark about that in terms of this particular system of equations. So our system of equations here consists of these 3 equations in the variables x, y, and z. So I want to make a remark about why it's called the augmented matrix, which might seem like a strange name to give it. The first observation is that that system of equations could be, if you wanted, you could write it as instead of 3 separate equations, you could write it as a matrix equation that would say that if you take the column vector x, y, z, so x, y, and z obviously appear in all 3 equations, so those are our 3 variables, and if you multiply it on the left by the matrix, whose entries are 1, 2, minus 1, 3, 1, minus 2, so these are just the coefficients of x, y, and z in the 3 equations, read off from the system, minus 1, 4, 2, then what you would get in that would be a 3 by 1 vector, obviously, but its entries would just be the left-hand sides of the three equations in this system. And so in order for the system to be satisfied, that would have to be equal to 590, which is what's written on the right-hand side of the system of equations. So basically, this system of three equations in three variables can be written in equivalent form as this single matrix equation. So this is a matrix equation that says you've got this kind of unknown column whose entries are variable names multiplied by a specific matrix on the left, and you want that to be a specific matrix on the right. So one could attack this problem using the methods of matrix algebra if you wanted to. We're not going to really do that, but it's just a remark that one could. And in that context, this square matrix there on the left would be referred to as the coefficient matrix of the system. And that's a very standard term. Okay, of that system that we started with. Okay, so the reason for what we are actually going to write down is not exactly that coefficient matrix, but this 3x4 matrix, which has in its first three columns basically the coefficients of x, y, and z in the system of equations. And in the fourth column, it has the right-hand side, and there's a kind of line here, which doesn't really have a role in any calculations. It's just there to kind of indicate that the first three columns have a slightly different meaning from the fourth one. And some people, including me, find it kind of handy to carry that line around just to kind of remind themselves. So basically, the term augmented matrix, what it corresponds, what it refers to is that basically it's the coefficient matrix, which would be the first three columns, but augmented with the column corresponding to the right-hand side. So that's why it's referred to as the augmented matrix. And a remark about the augmented matrix is that its first bunch of columns correspond to the variables, in this case x, y, z. So the entries of the column that corresponds to x are the coefficients of x in the three equations, and the final column corresponds to about RHS for right-hand side. It corresponds to the right-hand side of the systems of equations. So the columns in the augmented matrix are sort of labeled by the variables, and the rows are labeled by the equations, and that's written in here already. Equation 1, equation 2, equation 3 correspond to the three rows. Okay, so remark about the augmented matrix is, if you know the context, then the system of equations as it's written here on the left and the augmented matrix carry exactly the same information. We've kind of, in writing down the matrix, we've kind of thrown away the variable names, we've thrown away the equal signs, we kind of understand that they're there in between the third and fourth column, and we've just kept the kind of essential information that defines this particular system, and that's the coefficients of the variables in the equations and the right-hand sides. So basically, if you know the context, if you know where this is coming from, you can reconstruct the system of equations from the augmented matrix. Okay, so somehow it contains kind of all the essential information that one would need in order to solve the system. And that, I suppose, is kind of the first key principle here. You're kind of throwing away the inessential stuff and keeping only the essential information that you need. And you're kind of organizing it in this kind of concise form into a matrix. Okay, so the operations that we were allowed to carry out when solving the system of equations by kind of what I refer to as ad hoc or sort of direct methods was we could multiply an equation by a non-zero constant, maybe with the goal of kind of matching the coefficient of some variable in two different equations and then adding them together or subtracting one from the other. And we could add a multiple of one equation to another equation. Okay, so what that translates to into the matrix is, so our matrix here has, in this example, three row vectors corresponding to the three equations. So if you were to multiply equation 1 across the way by 3, that would replace all the coefficients by multiplying them by 3. So we can multiply row 1 here in the augmented matrix by 3 if we want to. Okay, and that makes it correspond to a slightly different equation, but one which has the same system of solutions as the one that we started with. Okay, so we can multiply a row by a non-zero constant, and that means multiply every element of that row, every entry in that row, by the non-zero constant. Okay, we can add a multiple of one row to another row. Okay, and that corresponds to the operation of multiplying one of the equations by a constant and then adding it to another equation, and that new thing becomes sort of the part of our new system. And the third thing that we can do is interchange two rows in the matrix. That's something that we didn't refer to with the equations, but it just means reordering it means changing the order in which the equations are written, which certainly doesn't change their simultaneous solutions. So what we're going to do is we're going to consider these operations as things that you can do just to a matrix. okay, regardless of whether or not it has the context of belonging to a system of equations or being connected to one. But that is the motivating sort of situation. So we'll allow ourselves to do these types of operations on the rows of a matrix, and we'll refer to them as elementary row operations. Okay, and the sort of suggestion is that we can, by organizing these elementary row operations in a suitable way, that we'll be able to devise a reliable method for solving systems of linear equations. Okay, so to see how this method works, we're going to take this example as our kind of working example and work through it using this method. Okay, so bear in mind what the three elementary row operations are that we're allowed to write down. And here is our information from the previous examples. The next slide is called Gaussian elimination. And the process that we're about to go through essentially is what is known as Gaussian elimination. Okay, so we'll go through a few steps. We'll see what happens to our augmented matrix along the way, and we will figure out how what we're doing enables us to identify the solution or solutions of the system of equations. So here we are. This is the same example as last time. It's written slightly in a different arrangement. So here's the system of equations that we're starting with. And our problem is to solve this system of equations. So the approach is organized into kind of a table, step by step. I don't expect you to write a table like this every time you tackle a problem like this, but it's meant here for sort of illustrative purposes. But it is useful to devise some kind of method of keeping track of what you're doing, so that you can, so that you can sort of follow your own steps and, if necessary, retrace them in order to find any accidental errors that could occur along the way. So here's our system of equations. This is the starting point. So the problem that was given to us was solve this system of equations. First step, write the augmented matrix. Okay, so, and we're going to identify a series of elementary row operations that we can carry out on this augmented matrix that will enable us to solve the system. Okay, and remember what the elementary row operations we can do are: we can multiply a row by a non-zero constant, we can add a multiple of one row to another row, and we can interchange two rows if we want to. And so on the left-hand column here of this table, we're going to keep track of what elementary row operation it is that we're applying at each step, and we have some notation for that that I'll try to kind of describe as we go along. So this is our first step. Okay, so focus on the augmented matrix. Here it is. Okay, and the first thing that we would like to do using elementary row operations is we'd like to transform the first column of this matrix so that it just has a 1 in the top entry and zeros below that. And the strategy for that is, first step, arrange to get a 1 in the top left. Okay, in this example, that comes for free. There already is a 1 in the top left. Great, so that's kind of a bit of a bonus, nothing to do to arrange that. And then when we've done that, the next step is to subtract multiples of row 1, or add multiples of row 1 to subsequent rows in order to eliminate the non-zero entries under the 1 in that first column. So at this stage, we're kind of focused on these two entries. Okay, we'd like them to be zeros. They're 3 and minus 1 currently. We're going to use the 1 at the top of the first column to subtract multiples of row 1 from rows 2 and 3 in order to get a 0 and a 0 where the 3 and the minus 1 are. So first, if we look at the minus 1 here in row 3. Okay, and what we need to add to that minus 1 to get 0 is 1. So we can add row 1 to row 3, and that becomes the new row 3. And the notation for that is we're going to replace the existing row 3 with row 3 plus row 1. Okay, that means essentially we're going to replace equation 3 here with the sum of equation 3 and equation 1. Okay, which doesn't change the simultaneous solutions of the system, because anything that satisfies the first two equations and the third one also has to satisfy the first two equations and the sum of the first one and the third one. Okay, so that's the idea. So at the level of the matrix, we're focusing on row 3. So we're looking here. For each entry in row 3, we're adding 1 times the entry above it in row 1. So we get minus 1 plus 1, that's 0 here. We get 4 plus 2, that's 6 here. We get 2 plus minus 1, that's 1 here. And we get 0 plus 5, that's 5 here. And just make sure when you're doing these operations that you go all the way along the row. It's a really easy mistake to make, to just sort of to not do that, to just sort of stop somewhere along the way. If you do that, you're of course going to mess up your system, because it means that you're no longer sort of adding one equation to another. You're only doing kind of part of that job. So just make sure that you always work the full way along the row. Okay, so bearing in mind this is still an augmented matrix, And it still corresponds to a system of equations. And just for this example only, I'm going to write down the system of equations at every step, just so that we can keep track of what we're doing and what we're saying. The first equation and the second equation haven't changed here, but the third equation has. Now it's 0x plus 6y plus z equals 5. Okay, so this is really the sum of the first and the third equation in the original formulation. Okay, that's fine. That's good. That's what we wanted. Next thing I said we wanted to do was get rid of the other non-zero entries below the 1 at the top of column 1. So to get rid of this 3, we must ask ourselves, okay, what do I have to add or subtract from 3 to get 0? The answer is I have to add minus 3. So I should add minus 3 times row 1 to row 2, and that would become the new row 2. And that's what this notation means. So this notation on the left, you don't necessarily have to use exactly the same as me to keep track of your elementary row operations when you're applying them. But I really recommend sort of having a notation, something along these lines that works for you and that you can follow and that you can use to identify what steps have been taken along the way if you need to look back at it a second time. Okay, anyway, what we're doing here is we're adding minus 3 times row 1 to row 2. So in the first entry, we get 3 plus minus 3 times 1, that's 0. Second entry, we get 1 plus minus 3 times 2, that's minus 5. Third entry, we get minus 2 plus minus 3 times minus 1, that's minus 2 plus 3, so it's 1. And fourthly, we get 9 plus minus 3 times 5, that's 9 minus 15, so it's minus 6. So the new second row of our augmented matrix is this row, and that corresponds to the equation 0x minus 5y plus z equals minus 6. And so the first and third equations haven't changed since the previous step to this step, but the second one has. Okay, and now our system of equations already looks kind of nicer. The second two equations only involve the variables y and z and not x anymore. And of course, that's exactly the situation that you expect after this first phase of clearing out column 1. You now have a bunch of equations, but the first variable only appears in the first one. So essentially, you've kind of, you sort of almost got a simpler system of equations in one fewer variables. If you can solve that one, you can certainly find the corresponding value of x from the first one, and that's sort of the theory. Okay, so that's where we are. So for the rest of it, I'm just going to go through it by hand, but still sort of building on this same table. Okay, so that's where we are. Let me leave that last stage of that hopefully still in view. Okay, so now we have to ask ourselves, what's the next elementary row operation that we'd like to apply? So at this stage, we're happy with column 1. We don't want to touch that anymore. And one important thing to bear in mind there is that at no future stage do we ever again want to add row 1 or subtract row 1 from any subsequent row, because that will mess up the nice pattern of 1s and 0s that we've already taken some trouble to get into column 1. So the next step is to move to column 2. Okay, to ignore the first entry in column 2 for now. Look at the second entry in column 2. Okay, we'd like that to be a 1. At the moment, it's a minus 5. So we can ask ourselves, well, what could we do to get a 1 there where that minus 5 is? And the answer is, well, we could add 3 times row 1, but we don't want to do that because that would also damage our 0 in the first entry of row 2, which we certainly do not want to damage. We want to keep that. So in order to figure out what we should do to turn that minus 5 into a 1, we should look below row 2 and not above it. We could, of course, multiply row 2 by minus 1/5, which would be fine, nothing wrong with it, but it would have the kind of annoying feature that it would lead us to having sort of fractions in our matrix, which might be awkward or inconvenient to deal with as we proceed through the calculations. So something that we can do with row 2 that would not have that problem is we could add row 3 to row 2, and that would give us a 1 there where the minus 5 is, because it would give us a minus 5 plus 6. So next operation is to replace row 2 with row 2 plus row 3. And the only motivation for that is to get a 1 there where the minus 5 is. Okay, so when we do it, we're not changing row 1. So we still have 1, 2, minus 1, 5 in the first row. The second row we are changing, and at every stage we're adding the entry in row 3 to the entry in row 2. So first we get 0 plus 0. That's always going to still be 0, because that 0 in position 1 of row 2 only has zeros below it. We have minus 5 plus 6, that's 1. We have 1 plus 1, that's 2. And we have minus 6 plus 5, that's minus 1. So that's what we get in row 2. And then in row 3, we have not changed that, so we get whatever we had before, 0, 6, 1, 5. Okay, this is step number 3 in the elementary row operations. Okay, good, this is progress. Well, it is progress, at least if you believe me, that what we wanted was a 1 there in the first in the second position of row 2, what we'd like to do now would be exactly as we did for column 1. We'd like to clear out the rest of column 2 below that 1. So we'd like to have a 0 where that 6 is in row 3. And we can do that once we've got our 1 in position 2 of row 2 by just subtracting or adding multiples of row 2 from subsequent rows. So our next step is going to be, this is number 4 in our series of elementary row operations. We're going to eliminate that 6, we're going to turn it into a 0, and we're going to do that by replacing row 3 with row 3 minus 6 times row 2. And when we do that, again here at every step, I mean you can roll multiple steps into one sort of written step if you want to, but in principle at every step we're changing one row, and the other ones are left unchanged. Of course, if you apply an operation of swapping 2 rows, then you change 2 rows by just swapping them. But otherwise, operations of this type, adding a multiple of one row to another row, only change one row, and same for the one where you multiply a row by a constant. So this one is going to change row 3, but it's not going to change row 1 or row 2. The way that row 3 changes is it has 6 times row 2 added to it. That doesn't affect the 0 in the lower left. That, of course, is deliberate, not accidental. It's because we already have a 0 in row 2 above that 0 in row 3. Second position, we got 6 minus 6 times 1, that's 0. That's what we want. Third position, we've got 1 minus 6 times 2, that's 1 minus 12, so it's minus 11. Fourth position, we've got 5 minus 6 times minus 1, so we've got 5 plus 6, which is 11. Okay, final step. This is not, at least for this example, same story. So now row 1 and row 2 are sort of considered to be kind of done for the moment at least. And column 1 and column 2 have this feature. So in row 1, we have a 1 as the first non-zero entry. And below that, we have only zeros. To the right of it, we have other entries. Then we look at the entry in row 2, column 2, arrange for it to be a 1, clear out below it, and then you move on to the entry in row 3, column 3, which is here. It's minus 11 currently. So we'd like to arrange for that to be a 1 without damaging the pattern of zeros that we've gone to some trouble to arrange there. So at this point, we can't add any multiples of row 2 or row 3. Pardon me. We can't add any multiples of row 2 or row 1 to row 3 because that would damage this little sort of triangle of zeros that we have arranged there, which has been sort of our whole kind of mission so far. So if we were to reverse that, we'd be kind of just going around in circles. But what we can do with row 3 to eliminate that minus 11 and make it into a 1 is we can just multiply it by minus 1 over 11. And that for this example, of course, because this example was chosen to have a sort of nice solution, gives us a relatively nice form. 0, 1, 2, minus 1 in row 2, and in row 3, we're multiplying by minus 1 over 11, so we get 1 here and minus 1 here. Okay, and so, of course, at this stage, we've eliminated the variable x from both equation 2 and equation 3. We've then eliminated the variable y from equation 3. So the new equation 3 only involves the variable z, and it tells us what the value of z must be in any solution of our system of equations. So in any simultaneous solution of the first 3 equations. Okay, so our system of equations, which has been adjusted at each time, this is how it reads now at the end, at this point. Okay, so first equation is the original first equation. That didn't change, I think, at any stage. Second equation involves only y and z, and the third equation involves only z. So I guess most people would probably agree that this is a simpler system of equations than the one that we started with. But it has the same solutions, because at all stages, we applied operations that didn't change the simultaneous solutions of the system. Okay, the advantage of the new version, of course, is that it has its solutions are easy to write down. So here's our new system of equations. This is easily solved relative to what we started with, and solved by the method which is referred to as back substitution, which is, well, it's arguable whether this method really needs a name, but it does have one, and it's back substitution. So yeah, I mean, it does what it says in the tin. The third equation now has only one variable in it, so it's just a statement of the value of that variable in a solution. Substitute that back into the previous equation to get a solution for y, and substitute both of those back into the first one to get a solution for x. So that's how the back substitution process works. Equation C tells us z equals minus 1, so that must be true in any solution of the system. Equation B now says y equals minus 1 minus 2z, So for a solution of the system, z has to be -1. So y has to be -1 minus 2 times -1, and that is 1. And then equation A says x is 5 minus 2y plus z. So for a solution, x must be 5 minus 2 times the value of y plus 1 times the value of z, so it must be 2. And so our conclusion is that the solution of this final system, and therefore also of the original one, is x equals 2, y equals 1, z equals -1. And this is the only solution, both of the final system and of the original one, and every intermediate one, since no operation that we took at any step along the way changed the simultaneous solutions of the system that we started with. Okay, so that is how, so the technique that we just used is referred to as Gaussian elimination with back substitution. Okay, so a few more kind of comments about it, and this is sort of partly about terminology that's technical but important for us. And the first piece of terminology is referring to something called the row echelon form. So this was the matrix that we ended up with. It was the augmented matrix of the last version of the system. Okay. And we say that it's in row echelon form. Okay, so that kind of covers a few things. One of the things that, so a matrix is in row echelon form if its entries are arranged in a way that satisfies certain rules, or if its entries satisfy certain rules. And so what it means to be in row echelon form if you are a matrix is that in each row, the first non-zero entry must be a 1. Okay, and that is referred to as a leading 1. So you could have a row that's all zeros. But in any row that isn't all zeros, the first non-zero entry must be a 1. And those particular ones that occur as the first non-zero entries of their rows are referred to as leading ones. And of course, there can be other entries that happen to be equal to 1, but they're not leading ones. So in this example, certainly yes, in row 1, we can confirm that the first non-zero entry is a 1. There it is. In row 2, the first entry is a 0, but the first non-zero entry is a 1. And in row 3, the first 2 entries are zeros, but the first non-zero entry is a 1. Fine. Okay, great. So second remark, or second property of a row echelon form is that if you have a column which contains a leading 1, and in this particular example, the leading ones are all circled in red now, so the columns that contain leading 1s are columns 1, column 2, and column 3. Then any entries in that column below the leading 1 must be zeros. Okay, so for example, in column 1 here, we have that leading 1, and here we have 2 zeros underneath it, so they are required to be 0 for a row echelon form. The third leading 1 is already in the last row, so there's nothing under it, so that's okay. Okay, but any 1, which is the first non-zero entry of its row, must have only zeros below it in the matrix. Okay, third stipulation is that as you move downwards through the rows of the matrix, the leading 1s should move from left to right. So basically, you can't have a leading 1 in row 3 to the left of a leading 1 above it in row 2. If you did have that, of course, you know, an elementary row operation could be applied to swap rows 2 and 3, and you'd be back to not breaking that rule. But yeah, but a condition for being in row echelon form is that as you move downwards, row 1, row 2, row 3, the leading 1s have to travel from left to right. They can't go from right to left. Okay, so it's not necessarily true that every row, sorry, that every column from the first one onwards must have a leading 1. I mean, it could happen that the first one has a leading 1, the second one doesn't, but the third one does again. Okay, and then finally, the last thing is that any rows that consist completely of zeros are grouped together at the bottom of the matrix. And so the process by which the augmented matrix of a system of equations was reduced to row echelon form there in our example is referred to as Gaussian elimination. And basically, any sort of process of applying elementary row operations to a matrix to get it into this type of echelon form is referred to as Gaussian elimination. And of course, you have choices to make potentially at certain steps along the way. You know, it could be that two people take the same matrix and apply Gaussian elimination to get it into row echelon form, but they don't necessarily apply the same step at each point. And indeed, they may not even get the same answer, and it's not necessarily true that they would, and they could both be consistent, but be different. One comment about row echelon forms is just to mention an example. You know, this is a very typical looking row echelon form, the one here. But another example of a matrix which is in row echelon form, which we'll abbreviate to REF for row echelon form. So here's an example with let's say 3 rows and 5 columns. So the first non-zero entry in column 1 must be a 1, and you can have anything to the right of that. So you could have 1, 2, 4, 0, 1, for example. That would be consistent with being in row echelon form. everything below this leading 1 must be a 0. So you could have a setup like that. Now, there could be a leading 1 in row 2, but it doesn't necessarily have to be in position 2. So you could have a 0 here, and then maybe have a 1 here, for instance. Okay, and you could have something in here and something there. Okay, if you have that situation, then you can't have a 1. Okay, the first non-zero entry in row 3 again has to be a 1, but we can't have a 1 here because the leading 1 in row 3 can't be to the left of the leading 1 in row 2. So this would have to be a 0. This leading 1 in row 2 in column 3 has to have zeros underneath it. So that would have to be a 0. The next entry basically can be a 0 or a 1. The first non-zero entry in row 3 has to be a 1. So if this entry is not a 0, it must be a 1. So let's say it is a 0. And then if this is, then the last one also can be either 0 or 1. Okay, so this would be an example of a matrix in row echelon form. And here, you know, when we talk about row echelon form, we are not assuming that these matrices, this matrix that was drawn there in that example, you know, it doesn't necessarily have to be the augmented matrix of a system of equations. It's just a matrix in its own right. So this definition of what it means to be in row echelon form is something that applies to any matrix. Okay, so that's an example of a matrix that is in row echelon form again. You know, it's if it had a 1 there under in the third or second position of row 3, it wouldn't be in row echelon form because it would fail one or more of these conditions. Okay, so that's what it means to be in row echelon form. And I guess, you know, it's a kind of technical definition that's kind of introduced in order to give us a vocabulary for talking about the process of solving systems of linear equations. It's handy to have a name for this thing. It's kind of probably good practice to get used to this definition and be able to recognize examples of matrices that are or are not in row echelon form, and to just sort of be familiar with that idea. Okay, so a general strategy, and this is the place where this is usually applicable, is if you are trying to solve a system of linear equations. General strategy to get a matrix into row echelon form is as follows. First step, get a 1 as the top left entry, and what you're allowed to do here is, maybe I should have said this in the title of the slide, what you're allowed to do is to use elementary row operations. Okay, that's the game. You can apply elementary row operations to some matrix, and your goal is to get it into row echelon form. So at the start, typically your matrix will have, you know, just some entries with whatever, they can be anything. First step is to get a 1 as the top left entry of the matrix. So get a 1 into this position. Okay, and of course, you know, the only case where you won't be able to do that would be if the column 1 is already full of zeros, which would be an unusual circumstance. If that happens, just move on to column 2. But if column 1 is not already full of zeros, you can get a 1 in the top left entry of the matrix. And, you know, possible ways of doing that, for example, if it isn't already there, would be if there's some non-zero entry already in that position, you can divide row 1 by that value to get a 1 there. That might introduce fractions, so you might not want to do it. Maybe you can swap row 1 with another row to get a 1 up in that top left entry, or maybe you can add a multiple of another row to row 1 in order to get a 1 in that top left entry. Okay, so at that point, the picture after step 1 is that you have a 1 here, and you have some stuff underneath it. So under that you have some stars. And the second step is to, once you've got your 1 in this top left position, to use it to clear out the rest of column 1 by adding or subtracting appropriate multiples of row 1 to all the subsequent rows, and bearing in mind that that affects everything in this area of the matrix. Okay, because you're going to be adding multiples of row 1 to subsequent rows. There are entries all along here, and so they're all going to have multiples of themselves added to these subsequent rows. So after step 1, the picture that you would like to have would be like this. You have a 1 here, you have zeros underneath it, you have some stuff here that you're not going to touch again for now. We'll talk about that in the next lecture. And now you have some stuff here in column 2. So after steps 1 and 2, your focus moves basically to these entries of column 2, not the first one, which is to the right of the first leading 1, but the rest of column 2. Okay, so the third step in the list here. So if column 2 contains non-zero entries other than in the first row, then your next goal is to get a 1 in position 2 of column 2. Okay, if column 2 happens to be already full of zeros, apart from possibly the first entry, then move on to column 3. Okay, that would be not the typical thing, but if that does happen, just move on to column 3. It means that column 2 is not going to contain a leading 1. So your goal at step 2 is as it was in your goal at this point when you've moved on to column 2 is much the same as what it was in step 1. You want to get a 1 here in the 2-2 position, the second entry of row 2. And again, ignore row 1 now, because we don't want to add row 1 again to any other row, because that would mess up our zeros in column 1. But look below this position, maybe you can add a multiple of some subsequent row to row 2 to get a 1 here in the 2-2 entry. Maybe you can swap row 2 with a later row in order to get a 1 in that 2-2 entry without damaging your pattern of zeros in column 1. And then once you've done that, same idea. Whatever is beneath that 1, clear it out by subtracting or adding multiples of row 2 from subsequent rows. Okay. When you've done that, your position then is that your matrix looks like this. It has a 1 here, it has zeros here. That's what you want. Move on to row 3. You could have some stuff here. Don't worry about it. Look at this position and try to get a 1 there, and then clear out column 3 below that 1. And that's the idea. Just work through the columns until a row echelon form is obtained. And this is something that I certainly encourage you to practice doing. And there are some examples like it in the current homework, of course. And it's it's a skill that kind of takes a little bit of practice, but certainly you can learn to implement it successfully. Just be careful about that you kind of do the calculations all the way along every row, and that you do them carefully so that you try to avoid mistakes. The trouble with it is, if mistakes made at some point, they can sort of propagate through the whole thing, so they can be quite hard to track down afterwards, even if they're just simple mistakes like sign errors or whatever. Okay, that is the strategy for obtaining a row echelon form in general. And at the moment, our strategy for solving a system of linear equations is to write down the augmented matrix. Okay, that would be a matrix whose number of rows would be equal to the number of equations, and whose number of columns would be 1 more than the number of the variables. We'd have 1 column for each variable and an additional column for the right-hand side. And basically, to reduce it to row echelon form using Gaussian elimination. This is a general description of how that goes, and the example hopefully sort of is useful as a kind of practical indication of how it works for a particular example. Okay, that example is fairly typical, but there are other kind of outcomes that are possible, and we'll talk about those in the coming lectures. And the other thing that we'll talk about in the coming lectures is, in the end, when your matrix is in row echelon form, basically it means that you have this kind of pattern of leading ones that goes more or less from top left in a sort of diagonal and downward pattern to the right as you travel down, not necessarily in a straight diagonal all the way down, but often it is that way, but it doesn't have to be. But we have this sort of line of leading ones, and below that and to the left of it are only zeros. But there still are lots of non-zero entries above it and to the right. And we will think later about what we can do with those, if anything. And what the answer to that is, we use a slightly extended version of Gaussian elimination, which is called Gauss-Jordan elimination, that we can do. We can clear out some of those entries above the leading ones as well. Okay, that's all coming in the next couple of lectures. That's it for this one. So thank you very much, everybody, and see you soon.